Alright, so the next day of derivatives. So remember last time we discussed the notation for derivatives. This is read f prime of x, y prime, or you could simply say dy dx. And you know, this y and this x can change based on like the letters in your problem. Like for instance, sometimes you have a function, let's say you have something called, you know, p of t, because it's about population over time or something like that, and you have your problem. So then you would see something called, the derivative would be called dp dt. All right, so the bottom variable is always the independent variable, the one in your function, and then the top is always just like the name of it. So that could change based on your situation. All right, remember that your derivative, it means your change in y over your change in x, your slope at any point or any time, any x value, your velocity of an object at any particular moment, it's your instantaneous velocity, and the slope of a tangent line to a function at whatever point you're talking about. So you also learned how to do the limit definition of a derivative right here last time. So let's practice a couple of limit definitions of derivatives before we go on, and you know, you can only appreciate the tricks if you can do things the hard way. So here we go. So remember what we did here. If we're using our limit definition, we set up a limit as h goes to 0. Big fraction, because we need f of x plus h over here. So I need to put x plus h right here. So negative 5, x plus h plus 7. All right, and then minus f of x. Remember, I'm subtracting this. So when I subtract it, it's going to affect the signs. So minus a negative 5 is plus 5x, and minus a 7. All right, all over h. All right, so then we go down, and I know it's annoying, but you got to write limit every time. All right, so some things I can see here. I'm going to have a negative 5x and a positive 5x. That's going to go away. All right, then I'm going to have a negative 5h. It's not going anywhere. And the 7s are gone, right? So that negative 5x is going to be gone. There's only going to be a negative 5h. Out on the bottom is an h, so I guess I didn't need this big fraction. All right, so these h's cancel. I have the limit as h goes to 0 of 5, negative 5. And so there's nothing to plug in. I don't have to plug in 0. So my answer is just negative 5. The limit of a constant is that constant. So there we go. But, you know, all along we knew that the limit was going to be negative 5. I'm sorry, the derivative was going to be negative 5 because this is a line. The slope is always negative 5. Right? So when you have a line, you know, your derivative is the same all the time. Whereas if you have like a parabola, your derivative is changing. Right? It's always changing, kind of always different. So our answer for the derivative is going to be more of a formula for calculating the slope. All right, so here we go. So I think I'm going to do this ahead of time. I'm going to do f of x plus h ahead of time because that's going to be a lot of work in my problem. So 2x plus h squared minus 3x plus h. And then when I get the answer to this, I'll just be able to plug it in the formula. All right, so this is going to be x squared. X times h times 2, so 2xh plus h squared minus 3x minus 3h. All right, so I'm going to have 2x squared and no other x squareds. I have 4xh and no other xh's. And let's see, plus 2h squared minus 3x minus 3h. All right, here we go. So that's going to be the whole front part of my limit. So I have the limit as h goes to 0 of this, and why don't we go ahead, instead of writing it all again, it's going to be that minus the original. So I'm going to be subtracting 2x squared minus 3x from this. So if we can just imagine. So look, those 2x squares are going to be gone. So those will be gone. I have a negative 3x is going to be a plus 3x. That's going to be gone. All right, so here's what I have left. 4xh. Let's see, plus 2h squared and minus 3h. Okay, all over h. All right, so everybody has an h. Let's cancel it. So I get 4x plus 2h minus 3. And I didn't really need a fraction, so I'll just put a 1 right there. Anyway, plug 0 in here. So if I plug 0 in for h, this is gone. So my answer is 4x minus 3. So this is the formula for the slope. So that means my slope is 4x minus 3. Okay? Whereas up here, my slope was negative 5. Okay, all right, so this is a formula for the slope. So any x value you tell me, I could like plug it into this formula and I could tell you the slope at that place. Okay. All right, so that's obviously very time consuming and tedious, right? So, oh no, hang on a second. I have to run and get something, a piece of paper. So there was like another page I was gonna do and I didn't have it on here. All right. Hang out for a second. I don't think I can pause this. Let me see. Let me see if I bring up a picture here. Just give me a second. Just fast forward the video. Let's see. Where is it? Day 3. All right, so you don't have to write this down, but I was just going to show it to you in this format. I didn't want to Xerox it because or copy it because it added another page to the notes. But anyway, so you don't have to write these things down, but I want you to notice like a little pattern that's going on here. So let me write a few of these down so that you can, we can talk about it. Again, just fast forward to when I start here. All right, so let's get started here. So we don't want to always have to do that limit definition of a derivative all the time. It can be quite tedious, and look, when you start getting x to the third, plugging in x plus h to this problem would be horrible. All right, so let me start doing some derivatives for you. So here's my derivative over here. All right, I have a line. It's at 2, so y equals 2. I know that the derivative of that would be 0. Here is a linear function. The derivative of this is always the slope, 5. So those are kind of like basic, they're kind of intuitive, you know, based on the picture. But here, f prime of x, watch what happens. This one is going to turn into 8x, and this one's going to turn into 5. And let me do the next one, and then let's think about it. This one. So the derivative of this part is going to be 6x squared. This part's going to be negative 12x. And this part's going to be nothing, so I'm not going to write anything. And the next one, see if you can figure out the pattern. So this is going to be 4x to the third. So notice something with the exponent and the leading coefficient. Next part's going to be 15 and x squared. The next part's going to be minus 8 and an x. The next part's going to be 3. So I hope you kind of saw what I was doing there and kind of got a little clue as to like the formula or the pattern that was happening. I was multiplying the exponent by the coefficient. So you multiply those, then you take one away. Because remember how I was saying before that derivatives always drop down a level? Well, a cubic becomes a quadratic. Okay, so 6x squared. This became negative 12, and then x to the first. This one, the 4, has no x, so you can think of it like this. It's a constant, so its derivative is 0. Or you can imagine there's an x to the 0 power. I could write that there, and 0 times 4 is 0, and so 0. All right, here, 8. Put the x down to x1. This has a 1 here, so 5, and then take 1 away would be no x at all. Okay. All right, so that's the idea. So you multiply the exponent by the leading coefficient, and you take 1 away from the exponent. Okay. So we get some different ones. So when it's negative, it kind of is a little bit strange. So I get negative 6, and then take 1 away from negative 2. That would put me down to negative 3. All right, plus half of 6 is 3. But if I take 1 away from 1/2, I get negative 1/2. And this is a constant, so there's a 0 there, so that's just nothing. All right, so f prime of x here. So if I ever have something in a fraction like this where the x is on the bottom, I have to fix it. This is really 4x to the negative 3. You can't, there is a way to do that, but it's much longer, and so why not just write it like this, and then it's easy. This part, a cube root. I don't know what to do with that. I need to write it as an exponent. So minus 12x to the, remember this is power over root, so 1/3, and then plus 4x. So my derivative, I would get negative 12, x to the negative 4, because I'm taking 1 away. Then 1/3 of 12 is 4, so I multiply those and I get negative 4, x to the, I take 1 away from 1/3. Well, 1/3 minus 1 is negative 2/3. Okay. And then here there's a 1, so 1 times 4 is 4, and no x. Okay, so on your notes there, that is a rule that we have written down, and this is how it looks. So if you have x to a power, it's called the power rule. You multiply that n by the front, and then you take 1 away. So this is just the definition of the power rule. All right, so let's do that here. In fact, why don't you try it? You do this derivative, pause the video, and do it. All right, so you get negative 20, x to the 3rd, plus 6x minus 7. Okay, so that's the basics, and the only other thing you have to do is sometimes you have to fix the problem first. So in a situation like this, there is a rule for doing something, a fraction like this. It's called the quotient rule, but the quotient rule is a little bit difficult, so you'd want to avoid it if you can. So another way of writing this problem would be to literally break it up into 3 parts. There's only one piece down there. I could actually divide them. So 4 divided by 2 is 2. x5 and x2 divide to x3. Here, minus 2 divided by 2 is 1, and x squared is canceled out, so there's just a 1 here. And finally here, plus 3 over 2, and I have no x's here, but I have 2 on the bottom, so I have x to the negative 2. All right, so flatten your problem. You want to squish it down and flatten it, and then you can do the derivative. So that'd be 6x squared, a constant just goes to 0, this part. Negative 2 times 3/2 will be negative 3. The 2's cancel. And then x to the, take 1 away, turns into a negative 3. So you could write your problem like that, your answer, or you could write it as 6x squared minus 3 over x to the 3rd. You could write it like this as well. Okay. All right, so the next two are just some things like that. So again, we have to fix this. There is a way to do, like, it's called a product rule, so, but I don't need to do the product rule here. I could just like squish it together. I have 6x squared, and then this is an x to the 1/2. So let's fix it again. I still haven't done the derivative. I have a 6, x squared and x to the 1/2 make x to the 5/2, because 2 plus a half is 2 1/2, which is 5/2. So x to the 5/2. I have to get it like that so I can use my power rule. So minus 3x squared. Okay, so now finally my derivative. I just took the time to fix that. So 5/2 times 6. So 5/2 times 6, this cancels out to a 3, so I get 15. 15x to the, take 1 away. So 5/2 minus 1 would be 5/2 minus 2/2, or 3/2. And back here, luckily, we just got 6x. So there we go. Okay, and the last one here, if we're going to be able to use the power rule, we have to multiply this out. So let's multiply this out. 3x times x is 3x squared. I get minus 15x minus 1x. So that's minus 16x, and then plus 5. Well, that's these two pieces. I still have an x out here. So again, I'm still fixing the y. I haven't done the derivative yet. So my y is 3x to the third minus 16x squared plus 5x. So a lot of times it's better to fix your problem before using any other higher rule that you would have to deal with more problems, or it would just be harder. All right, so now my derivative, I'm ready. So I got 9x squared minus 32x, and then plus 5. And there's my derivative. Okay, that's it. See you in class.